Welcome to the Introduction to Algorithms lecture. So this is the first lecture in this course, and we will be discussing basically what is algorithms, what kind of algorithms are there, some philosophies behind them, and how do you measure the goodness or correctness of algorithms. To start with, let's ask the first basic question, namely, what is an algorithm? So an algorithm is of course a step-by-step process of doing a task. Now it can be any task as such. So you can have an algorithm for writing a program, to an algorithm for cooking a particular recipe, or so on and so forth. But let's ask, what is the first algorithm that you must have learned in your life? The first algorithm that is learned is usually how to add two numbers. Do you guys remember how did you do that? So the most obvious thing was that if somebody asked you what is the number 5 plus 2, you would put up a number 5 in one hand, number 2 in the other hand, and you add them up and you tell number 7. Now this is a very important algorithm because this is the kind of simplest algorithm that you can think of for adding two numbers. But very soon in your life, you or your parents or your teacher must have realized that this kind of algorithm has a restriction. Namely, you would not be able to sum up two numbers that are slightly bigger than 5. For example, how do you add up say two numbers which is say both are more than 10, say 11 plus 12? The problem is that in the algorithm for adding up these numbers using your fingers, you are restricted to just 5 fingers in each hand. So there is a restriction on number of resources that you have. So one way to do it is to add some more resources, and this is possibly what you had done in the beginning. Namely, you must have been taught to use this kind of areas somewhere like this. So this area is over here as 1, 2, 3, 4 to record more than number 5. So maybe here it is an example which is particularly used in many European societies to use the 4 fingers to record 4 into 3, namely 12 number 12. In Indian society, many times we use the 5 fingers and use the 4 markings, namely 1, 2, 3 and 4 to record 20 in each hand, so on and so forth, right? Now this is a big step forward in algorithms because you realize that this way of adding these numbers using fingers has a restriction, namely it has less number of resources, whereas this one has more resources. What happens if you want to add two bigger numbers? Say what happens if you want to add 53 and 49? Now here comes the problem. How do you add 53 plus 49? They cannot be counted in a hand or two hands. So we all know how did we do it, right? We were taught that okay, we can write 53, we can add 49, and what we do is that we look at the first digit, and here it is 3 and 9. We add 3 and 9 using some other technique like using our hands to count what is it. So it is 12, you write 2, 1 goes up as a carry, and you then add up the second digits and you get 10 and you write down 10. Right? So this is a very simple algorithm that we learned, because while we were almost made to memorize this algorithm when we were kids, and we had done millions of such summations in our younger days, but there are a few questions that I don't know how many of you have actually asked yourself properly. For example, does this algorithm always give the right answer? We always assume that that was the case. Say, so the first thing that we want to know is this statement, right? Why does this algorithm give the right answer? So in other words, what is the correctness of the algorithm, right? The second thing is that we had a simple algorithm of how to count two numbers, and now we had a slightly more complicated algorithm. Why did we do that? And of course, the answer is that the main goal was to reduce the amount of resources that we need. So if we had to count 53 and 49 by finger, by hand, or by sticks or something like that, it is not that it is not doable, right? Earlier days, people used to count 49 by drawing 5 lines and a strike, 4 lines and a strike to kind of count 5, and you keep on doing it, and after some few steps, you understand that you have counted 49. So you produce 49 sticks like this, and you then add up 53 more sticks and then count up the total number of them, and so on and so forth. So it is a possibility of how to count 53 by 49 without using this algorithm like this. But the main reason is that this technique of counting or adding up these two numbers is more complicated. Right? It takes a lot more resources. It takes a lot more time. So the difference between this algorithm on the right and the algorithm on the left, these two algorithms, is that one is taking more resources than the other. So almost from the very beginning of our life, we were made to come up with algorithms for doing simple stuff for like summations and so on, where the goal was to reduce the amount of resources made. But of course, a natural question is that do we have any can you quantify the amount of resources that we are saving? So how many resources are we indeed saving? So in this particular setting, we can say in a very nice simple way that if you do the simple counting, okay, by simple addition meaning say by hand, okay, if you have to sum up A plus B, then the total number of times you have to count will be basically A plus B, right? The number of steps is A plus B, because you will first count by finger in your hand or somewhere number A, then you add B one by one and look at A plus B. But when we use the addition by digits, right, the one that we are more familiar with or we are taught by adding the first digit and then taking the carry and the second, this to do A plus B, all I have to do is that represent A and represent B in the decimal format, right, and then add them up digit by digit. So the total number of digits that is required to write log A is nothing but log to the base 10 of A, and the total number of steps required to write B or digits required to write B is log B plus A. So in some sense, what you would be needing, the number of steps that you will be doing, is something of this form, some constants, and maybe for adding up any one digit you will need say 20 steps at most. So it will be something 20 into log A base 10 plus log B base 10. Now which is better? Is this a better number or is this a bigger number? So this starts the whole process of writing this whole thing, coming up with algorithms that reduces the amount of resources. Now, reduce, reducing resources is one of the main, of course, idea of algorithm. But here is a very simple algorithm and a simple problem. Namely, you have been given two numbers, x and y, and you can see these two numbers, and the goal is to check which number is bigger. Is it x is bigger or y is bigger? Now, one algorithm, so one of us comes up and says that okay, what I will do is that I will check all the digits from the left to right, and the first digit place where I see these two digits don't match, whichever digit is bigger, I will output that number as the bigger thing. Now see, kind of convince yourself that this is of course a correct algorithm, and the total number of steps required is basically of the order of uh, log the size of log x base 10 kind of stuff, right? Or if the total number of digits is n, then this becomes log 10 to the order of log n. But here somebody else comes up with a different algorithm. He says that I will be just be looking at the first 5 digits. If the first 5 digits, if I find a place where they are different, then I will of course output the one which is bigger, and if not, I will output y. Now, you can very well understand that in this particular example, this function will possibly give you the right answer, but if I had exchanged, I would have written this one as y and this one at x, my algorithm would have given a wrong answer. Okay, so here we are. We have this first algorithm that takes, sorry, I made a mistake over here, of course. I meant here that this will be order n. N is the number of digits, not order log n. And here in algorithm 5, it is just some number, total number of steps taken is something order 5, or which we basically say order of 1, right? A constant number of bits. So I have this algorithm 2 that has a number of steps is some constant, and algorithm 1 that the number of steps is order n. But on the other hand, algorithm 1 always gives me the right answer, and algorithms 2, does it give me the wrong answer all the time? Does it give me the right answer all the time? Does it give me the right answer most of the time? There are lots of questions that is coming up now. And I cannot say that which algorithm is better, because maybe this order n might be too costly an algorithm compared to an order 1 algorithm. It may be good enough to sacrifice some amount of correctness for the reduction in the number of steps. We are asking this set of questions. For example, we have kind of discussed how many steps are required by the algorithms, and the question is that are the algorithms always correct? And particularly look at the second question. This is an interesting question. That if x and y are two numbers randomly chosen from the set of 10 digit numbers, then what is the probability that the algorithm 2 outputs the correct answer? Maybe this number is high. So this is a question, okay, problem. You guys might want to take a look at. Can you give a correct number to this statement? So can you find the correct probability? So we have this two algorithms. One has a worse worse number of steps compared to the other, and in the other case, the opposite happens, which is basically the algorithm 2 doesn't necessarily always output a good answer, but maybe sometimes it does or many times it does, but algorithm 1 always gives the right answer. So we have these two kind of opposing forces that are acting on the algorithm. So I will go to a third question, and this is will kind of, I think, give you some more ideas about this algorithm such. So this is this problem of finding GCD between two numbers. So you know what is GCD, right? So GCD is basically the GCD of two numbers, say A comma B. This is the maximum, and I'm assuming at least in this slide that A, B, C, everything is a natural number. Maximum over all C such that C divides A and C divides B. Now, there are some very obvious ways of finding this GCD. We will come to that. I mean, we all know, right? You can just go over all possible C and you will get it. But if you recollect, there was some other algorithm that was also done. If you have forgotten, maybe you should kind of recollect what that algorithm is. Namely, you have this 48, you divide 20 by 48, and okay, it is 0. So you have 20, then you take this 48 over here, and you have 2, which is 40, then you have 8, then you bring that 20 over here, it is again 2, then 16, then you have 4, so these are all subtractions, right? And then you have this number which is 8, and 2, 8 and 0, and therefore we can say that this 4, we can use a different color, is the GCD between 48 and 20. So in other words, I can say that GCD between 48 and 20 is 4. So we have these two different kind of algorithms, right? So first algorithm is basically by the definition, and second algorithm is by here. Now I think almost all of you are familiar with the correctness of this algorithm. So I am not going to go into details of that. So in other words, both the algorithms gives the right GCD. But the question is that, can we pinpoint, or can you say why are we prefer this algorithm over this algorithm? I mean, you know the answer. It is to reduce the number of steps. But how much do we reduce the number of steps? Say, okay, so I have kind of written up this algorithm. So this is the algorithm for finding this GCD in the trivial way. So basically, if you are familiar with any programming languages, C, C++, anywhere, you would possibly understand this kind of writing. If not, I would request you guys to get familiarized with something that will make life easier. But also you might also realize that this particular way of writing this is not following any particular programming style. So this is not a code for a program. This is called a pseudocode. And this is what we will be using throughout the whole algorithms course. A kind of a step-by-step way of writing the algorithm, but not following any particular syntax or something. Right. So basically you can go over it, and what we are trying to do is that we are this y, sorry, there is a mistake over here, you might have understood this should be x, and basically it says that I am going to vary y from 1, slowly go up till y is less than a, and I will, as soon as I find a bigger y that divides both b and a and b, I would store that y as x. At the end of the day, when y reaches a, what does x, what is stored in x? The largest value of the largest number that divides both a and b is stored in x, right? So all we need to do is output x. So this is the pseudocode for the algorithm for simple GCD. And similarly here on the right hand side, I have written the pseudocode for the algorithm for finding the GCD in this slightly complicated way. So maybe I have not told you guys that this particular technique that I discussed or that we all know is called the Euclid's algorithm. And this is what is presented over here, the Euclid's algorithm. Fine. You can go over the pseudocode and now first statement that you have to convince yourself that I'm sure all of you kind of know is that both the algorithms are correct. But we also need a formal proof for, or rather give a formal proof of correctness. But there is one more step, the next important step. How many steps does the algorithm need? And here we have to be a bit careful. Now, what do I mean by how many steps an algorithm needs? Is it the number of steps in the minimum number of steps in the best? I mean, given up A and B, I can say that oh, the algorithm will always take only one step. At most, it will always take at least one step. Or is it that I can say that the algorithm will always take less than some number of steps? So in other words, am I interested in the minimum number of steps required by the algorithm? Or am I interested in the maximum number of steps required by the algorithm? And you can have the related questions, right? For what kind of pair A and B does the algorithm requires the minimum and maximum number of steps? And even more interestingly, the question is that what is the average number of steps required by the algorithm? Now, what is average means? Average over what? Average over maybe A and B when both A and B are numbers chosen between 1 and n and so on, right? There are various different structures that can be. Now, I will again let you guys go and think about them, but I will just say a few words about this one. What is the maximum number of steps the algorithm needs? Say I have to do this A, I have A and I have B, right? I have to do a GCD of A comma B. So what do? I will write A and I will write B over here and I will get the first statement, right? Or if I write it in a slightly different way, the first statement would be that I will write B as A times Q1 plus R1, right? Then I will write this A and R1. In other words, I will write this A to be equals to some R1 times Q2 plus R2. Right? And you can continue like that, right? You will then next write R1 as um, R2 times Q3 plus R3 and so on. You will keep on going till you hit something. Note that this R1, what do I have? I have that R1 is less than 8. I also have that R2 is less than R1. And I also have that R3 is less than R2. So in some sense, something is going down. But it is not going down. I have to quantify by how much quantity it is going down. So the important note thing that you need to prove is that, or I would write it as a note and I will let you guys go and think about it, is that this R2, so all I can say is that R2 is less than R1 is less than A, but this R2 is less than A by 2. So in other words, for every 2 steps, okay, after every 2 steps, this number, when you go from A to R2, the value is going down by a factor of 2. That means every time it goes down by a factor of 2, all these numbers are bigger than 1, of course. So the number of steps is, which means that maximum number of steps is less than 2 times log of A plus 1. Okay. So this is the running time or maximum running time between maximum running time for GCD. In fact, you can say something more. In fact, proves that the maximum or what we call as the worst case running time is upper bounded by 2 times the minimum of A comma B plus 1. Now, what is the best case running time? The best case running time is, of course, when A anyway divides B, you run it in one step, the algorithm stops. So, best case running time is 1. So, the best case running time is 1. The worst case running time is 2 times log minimum of A plus comma B plus 1. What is the average, what is the expected running time? So, if you want to study more on this Euclid's algorithm, it has a very nice Wikipedia page. I encourage you to go and look at it. There are a lot more stuff that has been done there. But this Euclid algorithm kind of gives us an idea about what this algorithm structures and everything are all about. So, in other words, to make this definition of algorithm a bit more complicated, the algorithm is a step-by-step process of doing a particular task, and the goal has just 2 goals. The first goal is the amount of resources required by the algorithm must be minimized. So, what do I mean by resources? They can be something like number of steps, they can be space, amount of space required, they can be amount of randomness required, number of samples required, and many of this stuff. Okay, throughout the course we will be seeing quite a few of these various resources. Also, even in the number of steps, there are not one particular way of seeing it, right? What is it? What is it trying to? You are trying to optimize. Is it the worst case step? Is it the average case step? There is something else called amortized steps. We will come to that slowly. So, on speaking from a very philosophical ground, algorithm tries to minimize the amount of resources, and they can be a multiple different kind of resources measured in a multiple different kind of ways. At the same time, on the other hand, the algorithm also tries to maximize the correctness. Correctness meaning correctness in the worst case, correctness in the approximate sense, correctness with high probability. So various kind of stuffs will be coming up. And this is why designing of algorithms has become so important and interesting. So it actually tries to solve various optimization problems at the same time. It minimizes the amount of resources required and maximizes the amount of correctness, and that's the goal, right? Now, before I stop this introduction stuff, let me just give you a few small details that will be required for setting our various problems later on. The first problem is called the input size. So, when somebody gives you a number or a input or data, there are various ways of presenting that number. For example, when I told that I will give the number 48, then one could have given me the number by drawing 48 sticks, right? So this is basically writing it as unary. Or you can write it as 48 as 1, I think 000. So this is in the binary. Or one could have given this 48 as just 48, right? This is in decimal. So there are these various ways of presentation. So we always are interested in, when we try to understand how good our algorithm is, we try to look at it, the inputs and the input size. So for example, in this setting, the input size is 48. In this setting, the input size is say 5. In this input size is 2. In fact, in case of 48, if we had written it in a slightly different way, say if we had basically told n, this n could have been written in the unary in order n size would have been the size of the input size, and in binary or decimal or any other mode it would have been order log n. So the input size is the size of the input. So n is not the input. So if we say that, oh, this number has been given to us, and usually when we talk about numbers, we think of it as given as in the binary or in decimal. So the input size is log n, not n. And usually the time complexity and space complexity is measured as a function of the input size. So we will say something like this function, the algorithm's running time is polynomial in the input size, or we might just say it's polynomial. It means that it is a polynomial in the input size, or polynomial in log n. Some places it will be, say, it is linear in the input size. It is a linear function of the input size. The linear function is log n. So this is the input size when it comes down to one particular number. There can be other ways of other objects that we might have to deal with in which different input size exists. But the important thing to note is that when somebody gives you an input, there is an input size, and the time complexity, space complexity, all complexities are measured in terms of the input size. Now finally, and this is a very important thing, how do you check the correctness of an algorithm? Or how do you convince or check the speed of an algorithm, the number of steps of an algorithm? So somebody comes up and designs an algorithm and gives it to you and claims that this algorithm is correct, or claims something that the algorithm is correct with probability 3/4, or claims that on expectation the running time is order n. So there are two ways of doing it. In the first way is the empirical method. Here you run the algorithm on a set of inputs called the benchmarks, and you verify the correctness or the running time or something in that you on that benchmarks. Sometimes in this setting you understand the speed of the algorithm by trying to understand the number of seconds after which the algorithm outputs the answer. Okay. But then we have to be very careful that are you running the algorithm on the similar machines, are you running on an older machine, so on and so forth. A lot of kind of things that has to be ensured that that have been normalized. The issue is this particular empirical methods technique is that it is easy to verify, easy to estimate, easy to run the algorithm, but it is not necessarily always correct. I mean, you all know that if a particular proof or a particular problem is true for most cases, it doesn't mean that it is true for all cases, right? If somebody comes and says that here is an algorithm that works for all functions or all inputs, and you kind of convince yourself that it has done for most of the inputs, it doesn't mean that the algorithm is correct for all the inputs. Now, this way of estimating or understanding the correctness of an algorithm is very common nowadays, particularly in machine learning literature and all, where many of the techniques are or algorithms are so complicated that coming up with a more formal proof of correctness, formal proof of runtime is hard to give. So people go for this procedure, and in some sense you have to accept it that this kind of stuff exists, but they also have their own problems, right? I mean, because it is easy to verify, because it is doable, so people use it a lot. The other spectrum is, of course, the more complicated one, which is the giving a completely mathematically rigorous proof. A mathematically rigorous proof of the correctness of the algorithm, mathematically rigorous proof of the time complexity or space complexity of the algorithm. So I'm not saying that this means that these proofs have to be correct all the time. I mean, the algorithm has to be correct all the time. The statement can be that this algorithm gives the correct answer with probability 3/4. It means that I have a mathematically rigorous proof that proves that the algorithm will be correct with probability 3/4. Okay. Now this is kind of the gold standard, if you can think of. This is the algorithm that works perfectly, no issues, very nice. But this is also much harder to prove. As I told you, many of the complicated algorithms that are now there in the neural networks and various other high level machine learning problems, we don't have the mathematical power to analyze them. We don't understand them well enough that we can analyze it, neither their correctness or their runtime. So this gives us a major dilemma. That we here one side we have the empirical methods, which are in some sense you can think of they are the cutting edge research, because they come up with algorithms that surprisingly works in most cases, but we don't have a reason why it should work, and it might fail. And there have been evidences of lots of examples where algorithms that have passed because of the empirical reasons have failed. I mean, I can tell you stories about it later on, but even this recent set of uh, plane crashes that happened was because of one such software. So they can be very costly affair also. On the other extreme, we have this mathematically correct proof which are kind of gold standards, but they are very hard to get by. But in this class of algorithms, we will be dealing mostly with the second type. This procedure, okay, this should be procedure 2 for the math. 2, yeah. Mostly with the second type. So this is what we will